Welcome to Astronomy with Mr. Mikulski. Today we are going to work on creating a scale model of a helium atom, and we're going to make that atom the size of a football field, or 100 yards across. The reason we're doing this is to practice and go through the process of making scale models so that we can eventually create a scale model of our solar system, also the size of a football field. Today we're going to take something that's very small and make it very large. And in the future, we will take the solar system, which is very large, and make it relatively small. Let's begin. In order to do this, we're going to need some information. So some of the data that I've already acquired, and you can look it up online if you'd like, is the helium atom specs. In other words, what are some of the sizes of the parts of a helium atom? So our objects that we're going to evaluate are going to be all looking at the diameter, so D for diameter of the helium atom, He. And when I looked that up, I have 2.5 times 10 to the negative 11 meters across. Within the helium atom, there are protons, so I'm going to have the diameter of a proton, and that is given as 1 times 10 to the negative 15 meters. And the diameter of a neutron, because there are neutrons in the nucleus as well, which is also considered to be 1 times 10 to the negative 15 meters. And then the electron, or electrons, that are kind of floating around out in the cloud are given a classical value of 5.64 times 10 to the negative 15 meters. Now, the data I collected is from the H-Twins website, Scale of the Universe Part 2. We've used that in class before, and I think it's just an easy resource to use for this information. Not really challenging its validity at this point, but I think these numbers are going to be good enough for us to use for this purpose. So ultimately, the goal here is a field which we know to be 100 yards across from goal to goal. And in that football field, we're going to throw the nucleus of a helium atom, which has 2 neutrons and 2 protons. And then floating around the outside somewhere in that cloud is what we have as the electron. And so the electron is what's determining the outer edge of our atom. And we're going to find out exactly how big that electron and the protons and neutrons would end up being on this scale model. And then we kind of find a little bit about how much space there may be inside of an atom. In order to do this, I want to create a ratio. The ratio is essentially the scale on which that I'm comparing, or I'm adjusting one object to fit into another. In this case, I'm going to say that 100 yards on my football field is now going to be equivalent to 2.5 times 10 to the negative 11 meters. So right now I know I'm mixing units, and that's a little bit messy. And also I have a very small number in the denominator. But this tells me for every 100 yards in real life, I would have 2.5 times 10 to the negative 11 meters in my scale. Or vice versa, I guess. The scale is the 2.5 times 10 to the negative 11 meters. I'm sorry, take that back. 2.5 times 10 to the negative 11 meters is the real life object, and I'm going to scale that to equal 100 yards. Essentially, this is like creating a fraction of 1 over 1. It's saying that these two are equal to each other because I've said that this is what I want them to be equal to each other, and so therefore I can use that ratio now to convert other measurements. Okay. So to do this, I really already know the size of my atom. My atom is, by definition, 100 yards across. Okay. So the next thing I can do is evaluate, well, if that's the size of the atom as a whole, let's say I put that nucleus on the 50-yard line, which you have on the football field. how big would the neutron or the proton end up being. So I'm going to go ahead and scroll down here a little bit. And at the end, I'll probably zoom out so you can try to see everything. I'm trying to do this all on one page. In order to calculate the size of the proton, okay, so we have our proton. I know that the proton itself is actually 1 times 10 to the negative 15 meters. This is my actual size of the proton. I need to take that actual size and multiply it by my ratio, which is the 100 yards per every 2.5 times 10 to the negative 11 meters. And so I have here, I'll write a little note that this is my actual and this is my ratio. And so when I multiply my actual times my ratio, I get my scale size. And so when we do this, we definitely need a calculator. And so go ahead and pull out your calculator and give it a try. Be careful with the scientific notation. I know that might be something to practice a little bit. And if you're not sure, please make sure to ask me. We can do that online when I'm available, or send me an email and I'll do my best. Maybe I'll make a video to explain that in detail by itself. When I do this calculation, one of the important things to notice is that my units of meters will cancel. Meters here cancels with meters here, and so I'm going to be left with units of yards in my answer. Okay, so I have 100 times 1 times 10 to the negative 15, and then divided by 2.5 times 10 to the negative 11. And when I do that, I get a value of 0.004 yards. If you got an answer anywhere near that, there may have been a little rounding there, but give yourself a pat on the back. That's pretty awesome. Okay. On a similar note, I can do the neutron. Now, since I know you guys are all awesome students, you'll probably notice that the neutron was the exact same size as the proton. So I can do the exact same thing again, or really, don't tell anybody, but you could just skip this step because nothing has changed. But I'm going to write it out just to be thorough here. So 2.5 times 10 to the negative 11 meters, just to show the thought process. Again, my meters will cancel, and so this would give me that the size or the scale size of my neutron is also 0.004 yards on that football field. Okay. In a little bit, we'll do a unit conversion to kind of get a feel for how big is 0.004 yards, because honestly, I don't really know, and I don't think it'd be worth knowing for you either at this point. Okay, next we can do one more, and that would be our electron. So the electron, we do have to do a little bit differently. Rather, we do the same process, but we're going to get a different number. And so now we're going to take the actual size of the electron. So that's my 5.64 times 10 to the negative 15 meters. And I'm still going to multiply by the exact same scale, or ratio rather, 100 yards over 2.5 times 10 to the negative 11 meters. So one of the things I want you to definitely notice about this process is that in all of these cases, the actual value did change depending on what that object was to begin with. But once I establish the ratio, once I know what that is, that's always the same. And so that is what makes this a little bit easier, because I can always do that process. You're just doing it over and over again. So it gets very repetitive, but hopefully it's not getting any harder. Again, my units of meters cancel, so I'll end up with yards as my answer. And for this, I get 0.0225 yards. And I think you might even get a 6 at the end there, so maybe we can round that to a 6. Okay. But somewhere in that range, I think will be okay. Now, I have these values. What does this mean? Okay, so I'm going to do a little conversion. We've got this magical thing called the Google, and I am going to, can I pause this? Okay, I guess I can't pause this. I'm going to go ahead and find out how big is 0.004 yards. So it turns out when I convert this, let's draw a line here. So convert, and this part's just extra. If I can spell the word convert. If I were to convert this, let's say, to inches, 0.004 yards is actually 0.144 inches in diameter. And so therefore, the diameter of a neutron would be 0.144 inches. And if that was the case, let's see. Of our electron would be 0.8136 inches. So what does this mean to us? If you were to take a helium atom, which has 2 protons and 2 neutrons, and stick it on the 50-yard line of your football field, that atom, or rather the nucleus of that atom, with all 4 of those parts, would have a diameter. Each of those parts would have a diameter of only 0.144 inches. So that's about 1/8 of an inch, a little bigger than 1/8 of an inch for each of them. So there's 4 of those things. Even if you put them next to each other, like in a line, in one row, that would still only make about 4/8 of an inch, or in other words, about 1/2 of an inch. So the entire nucleus of the helium atom is only about 1/2 an inch in size compared to 100 yards of the entire football field. And that 1/2 inch object, which is, let's say, maybe about the size of a quarter, probably even a little bit less than a quarter, maybe a nickel. That nickel that is on the 50-yard line of the football field is holding on to, so to speak, the electron. The electron is a little bit larger in size in the classical view, but that electron is orbiting or kind of going around in its cloud about 50 yards away, so that its total diameter is, again, 100 yards. And basically, all the space in between is the unknown part of the atom, the part that the electron may or may not exist. And so it could be empty space, or it could be what we call the cloud of electron. But basically, we consider it as empty space, especially if you think of the Bohr model of the atom that is like electron orbitals. Okay, so there's a lot of background on atoms that you probably didn't want to know right now. But the cool part of this is that we just created the model of a single atom. What I want you to do is take this concept, and we're going to try to apply it to a planet in our solar system, given some other information. And I'll get to that in the next video. Thanks for sharing, and we'll see you next time.